Welcome everyone to today's colloquium. It's my pleasure to introduce Zach Tatlock, who is finishing up his Ph.D. at UC San Diego. Zach's worked on a variety of systems touching on compilers, databases, web browsers, with a theme of proving them formally correct. This field has moved a lot in the last few years, in part thanks to Zach, and that's what he's going to tell us about today.
Thanks for the introduction. If there are any questions during the talk, please feel free to ask. Things are a lot more fun when they're interactive. So as Dan said, I want to talk about techniques I've developed to improve software reliability. As we all know, software mediates increasingly many aspects of our lives. We now have software running inside of our bodies, keeping us alive. Computation controls transportation. Nearly every vehicle we use employs computation in one critical way or another. Traffic control, power grid, stock exchange. All these things run on software. We don't just depend either on software to survive in the world of today. Increasingly, many of our efforts to build towards a better tomorrow are also built on top of software in terms of simulation or sensitive instruments or control. And if you take a step back and kind of survey the range of problems we're able to solve with software, it's clearly a miraculous artifact. It's just stunning. Unfortunately, as powerful as software is, it's also incredibly brittle. There's been a lot of recent public failures of software. Research done here and at UCSD demonstrated that the modern automobile is vulnerable to remote attack, allowing attackers to take over the car, send messages to the anti-lock brake system, engine control module, turn off headlights, etc. In the medical field, medical device recalls by the FDA, now over 20% of them are due to software errors. This is really terrifying when you consider things like heart pumps. More broadly, the National Institute for Science and Technology estimates that software errors cost the US economy nearly $60 billion a year. That could put quite a dent in the recent sequesters if we could divert those efforts. And of course, software errors don't just affect the US economy. At the end of last year, there was an erroneous exchange made on Sweden's stock market for a value in excess of 130 times that nation's GDP. So it's pretty serious. And what's really going on is that we're living in this world of whack-a-mole. We have these software errors pop up, and we hit them on the head, we try to address them, but we have no guarantee that another error isn't going to rear its ugly head over here, or that trying to fix another error isn't going to cause the initial problem to reappear. And so we end up in this endless reactive cycle, this ad hoc approach of discovering programming errors and patching them. Now, perhaps we shouldn't be surprised. As Dijkstra told us a long time ago, testing is only sufficient for showing the presence of software errors, never their absence. And so whenever exhaustive testing is impossible, our trust can really only be placed in proof. There was a paper by DeMille, Lipton, and Perlis, which sort of discouraged this idea as a fool's errand. But recent developments in the PL community have actually shown it's not a dream, and that these techniques are ready for prime time. In particular, the technique I want to talk about is using a tool called a proof assistant. And at a high level, what we do with these tools is we develop our system in a language that's easy to reason about, often a purely functional programming language. And at the same time, we develop a correctness proof, which shows that our program always does what we expect. Now, these proofs are huge, intricate objects, which themselves might be buggy. But what distinguishes this approach is that those proofs are easy to check independently with a small, simple proof checker. And this methodology has actually had a large number of recent successes. One of the most visible is the verified CompCert C compiler. So this is a C compiler which takes a large subset of ANSI C and compiles down to modern architectures like PowerPC, x86, and ARM. And what distinguishes it is that it formally guarantees that whatever the behavior was of the input C program, that's also the behavior of the output assembly program, the corresponding output assembly program. And a group at Utah, led by John Rager, actually recently developed this random testing technique for C compilers. And when they applied it to mature, really stable compilers used in critical applications like GCC, LLVM, ICC, they found hundreds of bugs. Guess how many bugs they found in the verified parts of CompCert? That's right, 0. Yeah, no responses, no bugs. So no bugs. And that's really a huge achievement because compilers are extremely difficult to get right. Of course, this technique doesn't just apply to compilers. It's also been applied in the context of critical operating systems like Cell 4, which is a microkernel, and through tremendous effort is actually also guaranteed to be bug-free. So we sort of have this hammer, where we can produce these proofs, we can guarantee that we haven't made any errors while implementing our system. Now,
this is asserting that you know what the spec is.
That's right, yeah. So I distinguish programming errors as situations where the code we write differs from the way we expect the program to behave. Now, our expectations might be wrong. So specification errors are a different class of error. We'll talk about that at the very end of the talk. That's also serious. But for a lot of the programs, a lot of the problems we're addressing, we know what the system ought to do, and we simply don't implement it correctly. So now we're left with this sort of odd tension. On the one hand, there's this hammer I'm telling you about. If we apply it, we can guarantee that we've implemented a program according to our intuitions. On the other hand, we all know we live in this world of ad hoc reactive program error finding and patching. So what's going on? What's separating these two things? Well, the unfortunate reality is that these proofs are huge objects that are extremely difficult to construct. And in particular, that bites you in two ways. The first is that doing the initial verification is extremely expensive. So in the case of CompCert, over 70% of the development effort is devoted to proof. In the case of Cell4, it took nearly 200,000 lines of proof to reason about a 9,000-line C program. And this is actually painting a rosy picture. The reality is that in terms of effort, the situation is far worse, probably another 1 or 2 orders of magnitude off in ratio. Even once you finish the proofs, you're not done. Because anytime you want to change a system, extend it, optimize it, improve it, you have to redo all the proofs as well. And in the case of CompCert, this manifests as a lack of optimizations. So there have been several papers in top PL venues, each concerned with the verification of a single type of optimization. If adding optimization to CompCert is worthy of a pop-up paper, we probably won't have a lot of optimizations. In the case of Cell4, an optimization to the RPC mechanism took nearly 20% of the initial proof effort to be added. So really what's going on is that it's hard to get started. It's hard to initially verify a system. And once verified, if we want to change directions, it's extremely expensive. And of course, there's an analogous idea in physics, right, which is inertia. Object at rest stays at rest. Object in motion along a path follows that path unless acted on by outside force. This is really a perfect metaphor for the problems we're facing. So I coined the term formality inertia, which represents the issues I'd like to address. In particular, that unverified software is difficult to verify. And once verified, it's really difficult to change. So there are two problems to address from formality inertia. The first is figuring out ways that we can scale up proofs, the initial proofs, for large software developments. And the second problem is how we can take these systems once verified and minimize the effort that's required to evolve them over time to satisfy updating requirements. And so today I'm going to talk about research that I've done which addresses both of these problems. We're going to start off by talking about a technique I developed called formal shim verification. And at a high level, what we do in formal shim verification is we architect our system in such a way that we can verify just the small security or reliability critical parts of the code, but in doing so, make strong guarantees about the behavior of the entire system. And this is going to allow us to scale strong formal verification techniques up to huge pieces of infrastructure. The particular example I'll talk about is a web browser I built called Quark. Quark is able to render modern websites, and I'll actually show you a video of it running later in the talk. But what distinguishes Quark is that it provides provable guarantees for several important security properties, things like address bar correctness, tab isolation, and cookie confidentiality and integrity. And I've also done work trying to minimize the effort that goes into reproving these systems when we update them. In particular, I'll talk about current work I'm doing with a junior student on a domain-specific language for reactive systems, which allows us to more easily implement Quark-like systems, but automate away a lot of the proof effort that was so expensive in that project. So we'll start off by talking about formal shim verification and move on from there. But really to talk about formal shim verification, I'm going to take a step back and talk just about formal verification and proof assistance in general. So these techniques all center around a tool called the proof assistant. In the case of the work I'm talking about today, we use the Coq proof assistant from INRIA. And to use these tools, what you do is you start off by expressing your system in a language that's easy to reason about. This typically takes the form of a purely functional programming language, like ML or Haskell. And once we've written our language in this system, we also need to specify what it means for that program to be correct. What are the behaviors we want to allow? What should the program do? And once we have these two pieces written and loaded up in the proof assistant, comes the hard part. You have to find some poor grad student who's willing to bang their head against the problem, often for years, trying to show the code always satisfies specification. And this is an interactive process. We'll actually see it at work here in a minute. But once you've paid the price, once you've done the work, you're able to extract the program you reason about and compile it down to machine code. So you're reasoning about the actual implementation, not a simplified abstract model of the system. Now, this is sort of a really high-level workflow of how these things work. But I wanted to show you what it's actually like to work on these systems. So let's zoom in on my Emacs window. If you don't like Emacs and Vim, that's OK. I speak both. I don't take sides. So we start off by writing the program we want to reason about in this purely functional language. In this case, I'm showing factorial. these are over piano numerals, right? So you take a number n. If that number is 0, the result factorial is 1. If n is a successor of some smaller number, its predecessor, the factorial is n times that predecessor. Okay? And you can tell it's purely functional because I chose factorial as an example. Once we've written the system, we also want to specify what it means for that program to be correct. So in this case, suppose we're concerned with monotonicity. And essentially what this says is that function f is monotonic if for any two inputs, a and b, whenever a is less than or equal to b, the result of applying f to a is less than or equal to the result of applying f to b. Now, that's a big mouthful. All it really means is that if you move right along the x-axis, you move up along the y-axis, right? So you're non-decreasing. Now, once we've written our code and we've specified what it means for that code to be correct, we need to then formally prove that the code satisfies those properties. And so we can claim that, and then we move on to interactively proving that the code satisfies that. Now, these are not interactive proofs like you might have studied in complexity theory. They're a little bit different. So to try to give you a flavor, I actually made a video of myself proving this theorem in Coq. So we start off with the point at the top of the buffer, and we load up the definition of the code first, and then also the specification. And now we enter an interactive proving mode. So we have this goal. We have to show factorial is monotonic. And that goal consists of sub-goals. We now proceed by applying tactics, which are sort of little proof scripts that transform the goal. Typically what happens is you have a goal, and you're applying some lemma whose conclusion matches the shape of the goal. However, the lemma itself might have its own hypotheses, which then become new sub-goals that have to be satisfied. It's kind of like chopping the head off the hydra. More heads grow back. But you go through the proof, and you keep chopping and hacking away. More heads keep growing back until eventually you get to the end. And when there's no sub-goals left, you've formally proved the property holds. And this is a proof spelled out in full detail from the axioms of mathematics up. And it really guarantees the code absolutely satisfies the spec. So this is great. But right away, we see there might be a few problems. The first is that browsers don't look like factorial. They are imperative programs. They react to their environment. They often don't terminate. And perhaps more troubling is that the specification for browsers are not simple mathematical specifications like monotonicity. We're concerned with things like cookies and domains, frames, et cetera. But worst of all is really these proofs. So even for a simple program and a really simple property, the proofs grow quickly, and they're opaque. It's not at all clear how a change in the code or specification should be reflected by a change in the proof. And so it looks like this methodology is doomed. We have to throw everything away, start from scratch, spend tons of effort. In the case of Cell4, it took 22 person years to reason about a 9,000-line program. And it really seems like our goose is cooked. After all, browsers are millions of lines of code. And it's not simple code. These are low-level, highly optimized components, things like JPEG decoders, HTML renderers, advanced JavaScript engines. And sprinkled throughout this code, these millions of lines, are accesses to sensitive system resources, things like the disk, network, and screen. And it's unclear for a given access point who that access is being performed on behalf of. So it's difficult to reason about. But perhaps worst of all, this code base is constantly changing. And so even if we were able to somehow freeze the view of a browser, take it offline and formally verify it, by the time we got done, it'd be completely irrelevant. So this is a problem that I wanted to solve or address. And I also wanted to finish my Ph.D. So it's clear I had to take a slightly different tack. So what I do is I start off by isolating all the potentially vulnerable components of the system behind a sandbox. Now, once these components are isolated, they're no longer able to do anything useful. So the next step is to introduce what's called a shim. You can also think about it as a wrapper or a reference monitor. And what that shim does is it accesses system resources on behalf of the untrusted code and interposes on interactions between those components. So once we've designed the shim and updated the untrusted components to work in this manner, now we only need to verify the shim to guarantee behavior of the system. And this technique is actually called formal shim verification. I presented it at the most recent Usenix Security Symposium. And it doesn't just apply to web browsers. In fact, we can take these 3 steps and apply them to any large untrusted code base as long as 2 things are true. The first thing is that we need to be able to re-architect the system so that it fits within this architecture. You need to be able to split out the untrusted components and have them operate through a shim. The second thing is the properties you care about proving have to be in terms of who accesses what resource when. So we're not going to talk about how the untrusted code works. We're just going to restrict when and how it gets access to different sensitive resources. But this actually includes a large class of components. We have implementations now not only of a web browser, but also a web server and an SSH daemon. And the key insight here is that we can guarantee security properties for large systems while only reasoning about a small amount of code. And furthermore, we're actually going to prove the actual code correct in these systems, not just a model. So that's a high-level abstract view of formal shim verification. But I want to give you a more concrete flavor and show how it applies to browsers. So we just discussed how browsers are a challenging case for formal verification. But why browsers? Why start there? What matters? Well, it turns out that browsers have become a really important part of our infrastructure. People use them for banking, investment. We have medical records and even treatments now that are mediated by browsers. People use browsers for all sorts of office productivity suites, private communications, messaging. Social networking, of course. You might have embarrassing photos, things you don't want your children, or for undergrads, you don't want your parents to see. And most important of all, of course, we trust browsers with our conference submissions. We don't want to lose those. Now, because of all these really important applications, browsers have also become an attractive target. There's actually a competition each year at the CanSec West Security Conference called Pwn to Own, where security experts are able to exploit up-to-date browsers and violate all sorts of security policies. And sometimes they even take over the underlying machine. And of course, the security community is aware of these challenges. There have been many architectures proposed, a lot of new policies and different defenses. And this work is great, but it's often unclear when those approaches have been correctly implemented, because the defenses themselves are complex. And so this is really a key opportunity to apply formal shim verification. We'd like to implement these defenses and guarantee that we got it right. So in the case of browsers, I did this in a browser called Quark. I'm going to bring back up the formal shim verification diagram. We're going to kind of go through each step and see how these pieces are instantiated in the case of a browser. So in Quark, the resources correspond to things like the user interface, access to the network or hard disk, or persistent storage. The shim in Quark takes the form of a browser kernel, which is quite like the browser kernel in the Chrome browser. The difference is that our browser kernel has been implemented and formally verified in a proof assistant. And we'll talk about that in a lot more detail in a minute. In the case of Quark, the untrusted components correspond to processes which are strictly sandboxed. In fact, their only capability is to talk to the kernel over a pipe, a Unix domain socket. And in Quark, there are two types of components. The first correspond to WebKit tabs, which are responsible for rendering content from the internet. WebKit's an HTML rendering browser framework that's actually powers Google Chrome and Apple Safari browsers. And in this case, I needed to dig into the WebKit code and modify it so that any access to a sensitive resource, like the network or disk or user interface, was instead modified to send a message to the shim and request that action to be done by the browser kernel on behalf of the tab. The second type of component in Quark correspond to cookie manager processes. And these are simple key value stores, each of which is responsible for the cookies of a particular domain. And I just wrote these in Python. Now, in general, there can be multiple instances of each of these browser types, of each of these types of components. And the kernel is responsible for coordinating between them and their interaction. So out of all these things, what really distinguishes Quark is the formally verified browser kernel. So let's zoom in on that and take a look at how it was implemented, how I was able to specify what it meant for this kernel to be correct, and how I then proved that. So the Quark kernel takes the form of a large message processing loop. Essentially, in each iteration, it's going to receive messages from components and respond to them, updating kernel state on the way. And each time through the loop, it calls this function kstep, which takes the current kernel state. Now here I'm just showing a projection of a few fields, in particular the currently focused tab and list of all tabs. Now the first thing kstep does is a Unix-style select on the pipes it has to the different components of the system. Once it gets a file descriptor, a pipe that's ready to be read from, it then sees what kind of type it is. Perhaps it's a command from the user, or maybe it's a message from one of the browser components. If we're reading from the user, we parse a command from standard input. We then match to see what kind of command it is. In the case that the user would like to add a new tab, we create a new tab object. We tell that tab to render itself. And then we add that tab as the currently focused tab and add it to the list of all tabs and return that updated kernel state. So this is sort of one representative path through the kstep function. In general, though, the user might send other commands, or components might send requests. For example, access to the network or to update the screen, et cetera. And if you sort of look, by exploiting certain notation mechanisms in Coq, we're able to write C-like code. It almost looks imperative, which is a nice feature I'll talk about in a little bit. Now, once we've implemented our kernel, we also need to specify what it means for it to be correct. And these specifications take the form of safety properties that are intended to mitigate attacks against the browser. So one example is we might want to mitigate phishing attacks. Phishing attacks are mounted by nefarious types in an effort to trick users into divulging their own secret information. And one technical way they might try to do that is by spoofing the address bar. So maybe you're at a website, it looks like it's good.com, so you're willing to hand out your social security number or your credit card information. But in reality, through some clever manipulation of the DOM, the attacker's been able to rewrite the address bar to something it isn't. You're actually at website evil.com, and you're being tricked into giving this information to the bad guys. So we want to avoid that. So we need to reason about the behavior of the browser. And we do that at a very low level. We consider the sequences of system calls that the browser kernel makes. And we call these sequences of system calls traces. And we'll see that they are extremely useful when we want to specify and prove things about the kernel. Now, these aren't arbitrary systems of sequence calls. We know they correspond to executions of the Quark kernel, which means they have a certain structure. In particular, that structure corresponds to successive calls to the k-step function. So let's see how we're able to use this structure when we want to specify something like address bar correctness. So to write down address bar correctness, we say for any tab, trace, and domain, if Quark could have produced this trace, and tab is a currently focused tab in this execution, and domain is what's being displayed in the address bar, then it must be the case that the tab's domain is domain. They always agree. We're actually able to specify several important security properties in this same style. So these include things like tab non-interference. We can formally guarantee that the resources that Quark is willing to grant access to for one tab can never be influenced by its interactions with another tab. We also have things like cookie confidentiality and integrity. So this ensures that cookies are only accessed by tabs of the appropriate domain. And address bar correctness and integrity. We just saw address bar correctness. Address bar integrity simply means that if you update the address bar, the user was somehow in the loop. You can't invisibly change domains and trick the user into thinking they're at a website they're not. So once we've written the code and specified what it means to be correct, we then need to show the code always satisfies these specifications. And this corresponds to the part where the grad students bang their head against the wall. In particular, proving these safety properties entails proof by induction over the traces Quark can produce. Now, because they're safety properties, they prevent the browser doing something bad. The base case is easy. If you haven't done anything, you haven't done anything bad. So that's out of the way. All the work really comes in the inductive proof. And the way that looks is you assume that you've had an execution up to some point, and all your properties hold. Now, your obligation is to show that if you take another step through the k-step function, that your properties will all continue to hold. And proving this essentially takes the form of proof by case analysis. So for every possible path through k-step, we ask what system calls that could add to the trace. And we show that if we add those system calls, all of our properties still hold. Now, luckily, I was able to leverage a lot of existing techniques from the programming languages community to carry out this proof. In particular, we use things like monads to encode effectful computations in Coq's pure logic. We use Hoare logic for using up pre- and post conditions of these imperative operations. We also use ideas from operational semantics to characterize the set of traces that we consider valid, that the browser is allowed to generate. And we use linear logic for reasoning about how resources are created and consumed. So normally in logic, if you have a hypothesis, you're free to use it as many times as you want. In linear logic, once you use a hypothesis, that's it, it's gone. And so this is useful for reasoning about things like the trace. We can make sure it's correctly threaded through all effective operations. And also things like file handles, making sure that we only write the file handles that are open. And once you close the file handle, it can no longer be written to. And a lot of this was inspired by work in Why Not. We reworked some of their tools, but it was a great resource to be able to build on top of. But the key insight is that by applying this methodology, we're actually able to produce a modern web browser, renders all the Alexa top 10 sites, while only formally verifying a small bit of code. And I've said this stuff about Quark being modern and rendering your websites. So actually, I wanted to show you a video of it working. And right away, we see that Quark's interactive, which is really the most important performance metric in a browser. It's worth taking a second to realize what's going on here. Every mouse click, every keystroke, every screen update, network request, cookie access, et cetera, all these things are flowing through a browser kernel, which was written and formally verified in a proof assistant in Coq. And when we first wanted to do this, it was not at all clear it would be possible to get this kind of performance. In particular, the optimizations that we adopted, often inspired by Google Chrome, have made a huge difference. So here's a search for Don Carlos. Quick plug for them. I get a free burrito every time I give this talk. You should go there. So now I'm logging into Gmail. You'll notice that I didn't have to put in my username or password. That's because cookies are implemented in Quark, and they work correctly. So once you log into a site, session cookie saved, in your login stays. And you can tell there's a full instance of WebKit here. HTML rendering is working, JavaScript's at play. Everything's behaving correctly. One thing you might notice, there's a blinking cursor that actually took a tremendous amount of work. So we had to figure out how to modify WebKit to do rectangle-based rendering. This is an optimization we adapted from Chrome, which also does this. And that is responsible in large part for the improved performance. We also have a few other optimizations that allow websites like Google Maps to work correctly. We get relatively smooth zooming and panning in the Maps application. And in general, Quark works on many websites. So we also have it here. Amazon's loaded up, as is Facebook. And I tested on Alexa Top 10. It works on those websites. But the key point is that we're able to produce a realistic modern web browser with a kernel-written approved assistant and formally guarantee several important security props for that implementation. Now, of course, Quark isn't perfect. There are plenty of features that we're missing. For example, we don't have things like access to the file system, support for sound, or browser history. But these are features that we believe could be added in a relatively straightforward manner without completely reworking the browser kernel specifications or proof strategies. There are more important properties, though, that we'd like to have, which involve finer-grained access. So right now, all of our security properties are stated in terms of tabs and cookie processes as the security principles. In reality, a lot of standard web security policies involve frames. And so we're unable to actually address those in this setting because our principles are too coarse-grained. However, we believe that in principle, it's possible to refine that and reason about finer-grained security principles and therefore more realistic security policies, but it would require substantial engineering effort. Another area where we'd like to improve the browser is ensuring certain liveness properties. Right now, the browser kernel is synchronous and single-threaded, which means that a misbehaving component can actually prevent the kernel from working. We could actually modify our proof strategy to support asynchronous I/O and then make guarantees that the kernel is never blocked servicing any particular component. So there are a few ways we can evaluate Quark. Perhaps most important, though, is the trusted computing base. So this corresponds to components in our system, a bug in any of which could completely invalidate our formal guarantees. In particular, the TCB for Quark has two classes of components. The first are fundamental, and these will never go away. Those include things like the soundness of the logic we're working in, the specification of our security properties. We assume that those security properties match our intuitions. When I say tab isolation, and I write down a formula, I assume that those things mean the same. The rest of the trusted computing base, though, corresponds to components that can eventually be verified. And in fact, all of these are currently active research. Those are things like the OCaml runtime, which we use to compile the programs we extract from the proof assistant down to x86, the tab sandboxing mechanism, as well as the underlying operating system. We can also consider the effort it took to develop Quark. So our security properties in total span about 150 lines, while the implementation of the kernel is a little under 1,000, and the proofs are about a little under 5,000. What's important, though, is that in comparison, WebKit's over 1 million lines of code. So we've avoided reasoning about all of that. However, there's still some trouble. One thing is that writing the initial prototype implementation of the browser kernel took about a week, but proving that it satisfied all the policies took about 8 months, which is better than previous efforts, but it's still painful. So after this experience, I was starting to extend the browser to add more features, but I realized that the approach was perhaps it could be greatly eased, or that it was more general. In particular, when I was going initially add cookies to Quark and later on add other features, things were way more painful than they seemed like it ought to be. After all, I'd already figured out how to reason about these isolated processes. I had this sort of message passing library built in. I knew how to specify behavior of the system. But the problem was that cross-cutting changes corresponded to a huge amount of manual proof effort to update things. Oh, yeah?
Maybe you're going to get into this, but I'm just wondering, you have a list of things that you have not yet done to have really a full browser. I'm wondering what the implications in performance or anything else would be in adding those things.
That's a good question. So if we make the resources finer grained, for example, that one dimension of adding it, that will add more overhead because we'll have more context switching through the kernel. Basically, if I have one tab and that one tab is making requests for all of the subcomponents, there's less overhead in a sense because all the subcomponents in the browser can take advantage of caching done at the tab level. if I have multiple tabs, that'll increase that cost a little bit. That might be mitigated, that would be mitigated to a certain extent by making the browser kernel multi-threaded or asynchronous, but I don't know those numbers. Other features to add, things like history or sound or file system access, should not substantially impact performance in any way. But making the resources finer grained, I think that could create more overhead interacting with the shim. Now this is a research prototype. I think it can be further optimized, so that might be acceptable in practice, but that sort of have to be implemented and measured. Sorry, I didn't ask this question. Did that answer your question? OK.
I'm sorry, I'm still hung up on the question of the specs. So the properties you mentioned seem all very plausible, but what leads me to believe those are enough, that there isn't some other nasty thing that I didn't think of that can be exploited?
Yeah, that's an excellent point. It's something I want to talk about a little bit in future work at the end. But briefly, in general, if there was something to which we could appeal to show that our specifications were sufficient, that they covered all the cases we needed to consider or something, whatever the thing is to which we're appealing would then become the specification. So really, it's a fundamental issue. It can't be turtles all the way down. There will always be some element of the system which we can't prove correct because it's our starting point. It's what our basic assumption about the world. In this case, our basic assumption is that these are the properties we want, and that's it. You can't verify your specs are good. If you could verify your specs are good, they'd no longer be specs. So all I can say is that these are properties that we have found useful, that we feel address a large class of important security issues, and we are certainly open to adding more of them. Does that address your question? In some sense, there's no way to know that your specs are perfect. If you did, they wouldn't be specs. And so the one thing I mentioned in future work are techniques to come up with specifications, non-verification techniques to increase our confidence that our specifications are good through things like testing or independent validation by objective third parties, things like this. So popping back to the DSL or motivation for the DSL work, one issue is that whenever you add a feature that's cross-cutting, it's expensive. And there are a couple reasons for that. One thing is if the new feature breaks existing invariants, you have to go through you have to update those invariants and go through all the old code and show that it satisfies the new invariants. Also, if the new feature requires a new invariant, you have to go back through all the old code and show that it always establishes and maintains the new invariants. And what's particularly frustrating about this is the updates to the proof are extremely shallow. They're sort of just out of reach of mechanization, automation. They're not terribly interesting things to prove, and it's very brittle and frustrating. So I started thinking about this and sort of what's going on. And the issue is that not only does the proof dominate our effort, but again, you pay for it over and over and over. So it's kind of like poor Sisyphus, who is forced to roll this boulder up a mountain, only to watch it roll back to the bottom and repeat the process. I sort of have a lot of empathy for this guy right before conference deadlines. It's really a painful place to live. And so I asked myself, what should the world look like? What do I actually want to write? And really, all I want to write down are the parts of the specification and the parts of the implementation that are relevant to my particular application. More importantly is what I don't want to write. I don't want to write any manual proofs. I like those to sort of come out of thin air. But now we're left with a gap. How do we get from this ideal world where we just write small parts of the system that are specific to our application, but still get the strong guarantees of the methodologies I've been using? And the insight we've had here is to construct a domain-specific language. But now we're left with a gap. How do we get from this ideal world where we just write small parts of the system that are specific to our application, but still get the strong guarantees of the methodologies I've been using? And the insight we've had here is to construct a domain-specific language. And this has two advantages. The first is that programs written this way are going to be a lot easier to write, implement, and verify. But perhaps even more importantly is that they allow even non-expert programmers to get the benefits of these systems providing strong guarantees. So I built this DSL called Reflex, and the domain we're really focusing on are reactive systems. So this is a system where there's a component that is interacting with a number of, there's a kernel that's interacting with another number of components, exchanging messages between them, interposing on their communication, and accessing resources on their behalf. Looks a lot like the Quark browser kernel. And so we want to specify these systems essentially there are three things we need to get down. The first two are what the components of the system are and what messages can be exchanged on the pipes between them. And the second thing is how the kernel responds for each component when it receives a message of any particular type. And that response can correspond to things like updating the kernel state, sending messages to other components, or accessing resources on behalf of those components. Now, this allows us to specify the structure of computations allowed in programs in this language. But we also want to give the user the ability to restrict those computations and specify which ones should be allowed. In the case of reflex, this takes the form of an extended version of regular expressions, which allows us to restrict which traces the program should be allowed to exhibit. And also, we're exploring using linear temporal logic, which allows you to capture liveness properties. It's unclear how much domain experts will be comfortable with linear temporal logic, but regular expressions are widely used by programmers. And so, as one example, we can encode simple policies, like there's never an access to some sensitive resource until the component's been authorized. And so this is useful in the context of something like SSH. I want to make sure I never give a terminal to a connection until it's authenticated itself. Now, what's really important, though, is that by restricting the domain of computations you can express and the policies the user can write down to restrict the behavior of those systems, we're actually able to automate a large amount of the proof effort. In particular, I've written a tactic library inspired by proof by reflection work, which is able to perform a sort of counterexample-driven proof search and automates a large number of simple security properties. So this can capture things like cookie confidentiality, integrity, and Quark, but it's not up to the task of automatically proving something like tab isolation. So the key insight here is that by restricting the domain of computations and the language of specifications, we can do away with a lot of the grunge work that goes into maintaining these systems and automatically provide strong formal proofs for all the coarse grained security properties we'd like to have hold. So that's a high-level view of some of the work I've done recently on mitigating formality inertia. But I'd also like to take a step back now and talk about some of my previous research, give you a flavor for more broadly what I've been up to. If there are any questions on this stuff, this is a good time for them. But yes?
I don't think of its reflex as anything other than an architectural design language, like Write or something.
Like
Our architectural design languages like Write or some of the other ones in that world, they do similar things?
So I'm not familiar. So the question is if I'm familiar, how does this relate to architectural design languages? I'm not familiar with architectural design languages. I guess this is executable. So you actually produce a binary that runs, and you can automatically prove it has these important properties. So I got into formal verification through the sort of door of verifying compiler optimizations. And this is a field that actually has a really rich history. It goes back a long time. McCarthy did work on verifying a compiler for arithmetic expressions way back in the 60s. There's been plenty of work on it since then in the PL community. But based on the table I brought up earlier, you might think everything's been done. After all, there's 0 bugs in this column. Well, the reality is that this is not quite an apples-to-apples comparison. Many of the errors found in traditional compilers like GCC and LVM correspond to bugs and optimizations. These are often optimizations which CompCert simply doesn't support. And so it's not quite a fair comparison. So let's take a look at CompCert in particular and see why maybe it doesn't have as many optimizations. So like most compilers, CompCert starts with a C program and passes it through a sequence of transformations to ultimately produce an assembly program. Now, what distinguishes CompCert is that each of these transformations is accompanied by a formal correctness proof, which demonstrates that the program before and after optimization have exactly the same behavior. And these proofs work by constructing what's called a bisimulation relation. And it's really a simple thing. All it says is that if the original and transform programs were in related states, so for example, at the beginning of time, everything's equal between these two programs, and the original program can take a particular action, then it must be the case that the transform program can take the same action to end up in states that are, again, equivalent. Now, at a high level, all this means is that anything the original program can do, the transform program can do as well. We also need to prove the inverse. So we just flip all the arrows. And what that guarantees is that the two programs together, this guarantees the two programs are indistinguishable. So if I have a black box you can't see inside, I tell you one program, the other is in there, and all you can see is the observable behavior. You can't tell the difference, because anything one program could have done, the other could have, and vice versa. Now, because all of the transformations in CompCert have these style of correctness proofs, we're actually guaranteed that the entire compiler is correct. So this is great. This is how we get the 0 bugs in that right-hand column. But unfortunately, it also means that it's very difficult to extend the compiler because we have to do these proofs. So what I did was I took CompCert, and I extended it with my own module called xcert. And I rerouted the compilation pipeline to pass through xcert. Now, a priori, it's not clear that xcert's correct. So this calls into question the correctness of the extended version of CompCert. So let's look inside xcert and see sort of how everything fits together. Like CompCert itself, xcert passes the program through a sequence of transformations. And each of these transformations essentially has 2 components. The first is a high-level rewrite rule, which corresponds to a pattern in a program defined, and what to replace code that matches that pattern, how to rewrite it. The second thing in these optimizations is a set of local proofs, which relate the find and replace patterns in the xcert module. The main result that I proved is that as long as we have all these local proofs, there always exists a bisimulation relation between the program before and after xcert transforms it. So this is great. We know xcert's correct. But it seems like we've really just passed the buck. Users aren't going to write these Coq data structures with these find and replace patterns and all these local correctness proofs. But fortunately, previous work I'd done in a tool called PEC, which is a program equivalence checker, is able to automatically produce exactly these xcert modules from user-specified optimizations. And what really distinguishes PEC is that it's able to automatically prove the correctness of a large class of sophisticated loop optimizations, things like loop unswitching, software pipelining, loop distribution infusion, loop induction, variable strength reduction, et cetera, by exploiting modern SMT solvers. And so once we've done this, we're guaranteed that the extended version of CompCert is correct. And we're left with a compiler that always preserves the behavior of the program under a compilation, but is also able to be easily extended by users who may not even have expertise in formal verification. Now, my interest in optimization started actually a little bit earlier in an optimization technique I developed with colleagues at UCSD called equality saturation. Traditional optimizers work by taking a program, considering a list of possible optimizations they can apply, picking one, and transferring the program and repeating the process. The way you can view this is as taking a program and exploring a single path through the space of equivalent programs. Now, the downside of this approach is that you have to make decisions early on about what path you're going to explore when you don't know what the consequences of later decisions might be. This is known as the phase ordering problem. Equality saturation addresses that difficulty by taking a program and instead of destructively transforming it, instead representing a subspace of programs equivalent to the input program. Once you've represented this subspace, you then select the optimal program according to a cost model, and thereby improve the performance. So there's a lot of stuff here. I'd like to chat more about it. Most importantly, though, is I adapted this technique for checking the correctness of compile optimizations. I was actually able to find previously unknown bugs in mature Java optimization frameworks. I've also done some work ensuring the correctness of the interface between Java programs and databases. Typically, the abstractions used by database query languages and modern high-level programming languages don't match well. The problem is known as the impedance mismatch problem. So I developed a type system to ensure that values flowing out of the Java program towards the database are phrased correctly in terms of the database's abstractions, and vice versa. Values coming back out of the database are used correctly in the host program. So this is all stuff I've done. Moving forward, though, the problem I really want to address is the challenge of doing fully formal verification and making these really strong guarantees. In particular, that involves mitigating formality inertia. So I feel like, to some degree, we're sort of in the assembly programming language era of formal verification with proof assistance. These proofs are tremendously intricate. They're really difficult to construct. And they're supremely brittle. Any small tweak makes them completely fall apart. And so 2 ways I want to address these problems and push towards more of a high-level language era of formal verification and proof assistance is by finding problems that force us to extend the verification frontier. So these include addressing systems where maybe we don't know necessarily what it means to be correct yet. We have to figure out how to formalize and reason about them. Or scaling up past previous approaches, taking large bits of infrastructure, which seem infeasible to verify on the face of it, and developing new approaches to guarantee their correctness. In particular, this has taken the form of identifying and verifying pinch points. So in the browser, something like the Quark kernel, or more broadly in the DSL, these sort of reactive systems, bring the property of that. Now, once I've developed new techniques to push that frontier forward, there's a remaining challenge, which is that those techniques are often not accessible by domain expert programmers. So the next step is to sort of package up contributions that have been made by extending the frontier in ways that can actually have the potential for impact in practice. And often this involves creating things like domain-specific languages or verified infrastructure or libraries that are accessible. So in particular, 2 projects I want to work on that involve pushing this frontier forward are high-level synthesis and verifying high-level synthesis tools, and also verifying the implementations of cryptographic protocols. So high-level synthesis is a design methodology used by electrical engineers and computer architects to design circuits in terms of high-level languages. So typically you take a C program and compile it down to a program in Verilog or VHDL. Now this is great because it saves the developer a lot of effort. The downside is that this is a very challenging compilation problem, and many bugs arise. So I've actually already collected several bugs in modern state-of-the-art tools offered by industrial design firms. In one example, a fast Fourier transform is miscompiled, and results are shipped out of the circuit before computation is done. This is scary if you think about FFTs being done in avionics software, for example. And if you actually do the lithography and ship out bad hardware, recall is extremely expensive. So I want to avoid that problem, and I want to adapt techniques that I've developed in the compiler verification world to this setting, things like translation validation. The other project I'm very interested in is formally verifying the correctness of implementations of cryptographic protocols. So there's been some great work done by Gilles Barth and others on a project called Certicrypt, where researchers are able to formally prove that cryptographic protocols are secure, in the sense that over repeated iterations, an adversary's advantage is bounded. This is great work. It gives us a lot of confidence that our protocols are well thought out, well defined, and correct. But it doesn't say anything about the high performance, low level C implementations we actually run. So I want to bridge that gap and show that the implementations that we depend on for processing our credit cards, social security numbers, et cetera, follow the protocol as they should. And both these projects involve bridging semantic mismatches. C typically in the formal semantics for C are typically single-threaded synchronous, and you talk about a program's behavior as the set of traces it induces. This doesn't mesh well with Verilog, where the semantics are extremely non-deterministic and concurrent. So that has some big challenges to bridge that gap. And it doesn't mesh well with the semantics used in the high-level specifications of cryptographic protocols. We're not concerned with necessarily a flat set of traces a C program can induce, but a distribution over those traces. So we need to bring in some probability theory reason about that. Now, these are 2 projects that I'm already gearing up on. They're really kind of well within, not well within. They are, will be a slight reach, but I'm very confident I'll be able to address these. Further on the horizon, I'm interested in how do we come up with specs and improve our confidence that they're right. A cynic might say that even perfect formal verification only guarantees the implementation enjoys the same bugs as the spec. So what are we really getting? So this is kind of a fundamental thing, because as we talked about earlier, we can't prove our specs are right. But there might be approaches we can take to improve our confidence. I also want to improve the tools we use to carry out these fully formal proofs. The DSLs are a great way to provide an interface for non-verification experts, but I still need to build the DSL. And the tools we have right now are extremely brittle and difficult to work with. I think there's a lot of opportunities to interact with software engineering and people working on different proof strategies from machine learning or proof search and AI to make this tool better. I'm also extremely interested in applying proof assistant tools in the context of education. So there's been some effort already to do this in the domains of programming language meta theory, et cetera. But I think there's also a great opportunity to apply these in discrete math class and logic and proof-based courses. So that's where I'm headed. But all this work would not have been possible if I didn't have a lot of great mentors and colleagues at UCSD. Everything that happened here was done in collaboration with amazing people. I've been really excited to work with, been very, very fortunate to have such wonderful friends. And I would love to come to UW and keep working with just as great researchers. Thanks very much for your attention.
So we have a few minutes for questions. Paul?
You didn't mention model checking at all. Where would it fit in this picture, and could it help, or is it useless?
So the techniques we're interested in doing often require induction, because we want to reason about we want to have these really rich properties. So you could formalize model checkers and implement a model checker in the context of a proof assistant and use it to try to automate away some of the proof effort. That hasn't been done yet, but I'd be happy to talk about those connections more offline. Right now we're interested in these large state spaces, in these rich properties that really require human intuition to come up with the right induction predicates and carry out the induction by hand.
John.
If I start with an existing code base and I design a set of shims to protect some resources, how do you know that the remaining code uses the shims and doesn't access the resources around the shims in some
So
existing way?
are you concerned with untrusted code escaping the sandbox, or are you concerned with side channels?
I'm concerned with the sandbox, I guess. But are there general mechanisms that can, in a practical sense, can easily guarantee that you are protecting the resources?
So in general, the idea with formal shim verification is that we're assuming the tab sandboxing mechanism is correct. There is active research on these sandboxing mechanisms. So moving forward, ideally what we'll do is actually formally verify the sandboxing mechanism to guarantee that there's no way the code can escape it. So there's been interest in that from, for example, the NACL team at Google with Rock Salt, where they collaborate with Greg Morissette. So the ideally you would actually formally verify the sandboxing mechanism. One thing that I think is interesting is that it's always hard to sort of prevent side channels. So it's unclear how we address those. But sort of for direct connections between untrusted components and sensitive resources, we'll just prove that there are none. Yes.
Sure.
Did the process of proving the fork kernel correct identify bugs in the fork kernel?
Yes, but not perhaps always in the way one might think. So a lot of bugs were actually found in the specification. It was too strict. So there would be times where there'd be some execution where a tab really needed to access a resource in a certain way, and the specification was overly conservative and it would prevent it. So a lot of times it involved very carefully reasoning about how we need to loosen up the specification to allow correct functioning of the browser. There were also bugs in some of the message processing on an early prototype, but those were quickly fixed. You can't reason it. Like the proofs wouldn't go through at all. Yeah. Did that answer the question? Or? Okay.
All right, well, with that then, let's thank Zach again.